Hey, welcome back. Good to see you again. We're working with that continuous data set again, only this is part 2, and we're looking at the spread. Let's write that down here, how spread out the data is. Okay, and I've got these 4 diagrams here, or graphs of data sets, and I wanted to have a look and see if in just one figure, if I gave somebody one statistic that I calculated, it would indicate to them what was going on with the spread. Now here's a new one for us. You might have seen this in junior maths. This is called a stem and leaf plot, and we'll be talking about those later on. And how do you describe to people the best way of how spread out the data is when you've got a graph like that? Or the bimodal one again. Would it be practical to take the range, the max minus the min, the range in there? Would that give the correct impression if you're just quoting that one statistic? Remember, a statistic is a value calculated from a data set to indicate something. We've had mean, median and mode for the centre. Now we're looking at range and a couple of other things as well. What about this one down here? How would you indicate the spread of that? Would we include these, which would give the indication of a bigger spread? And that would be a range if we took the max minus the min, wouldn't it? Come to that, and again, this one here, almost a symmetrical distribution. Okay, so what we're going to do is look at different ways of describing to people how spread out the data set is. Just remembering that most people don't want to see a whole range of numbers, a whole set of numbers. We've got to précis it for them. We've got to describe a little bit about what's going on there to help them understand masses of figures. Come down now and let's have a look at the definitions here. And these screen clippings are from Hayes and Harris publications. And there we are. We're measuring the spread of the data set. The obvious one is the range. And the range is the maximum data value minus the minimum. And you might see some problems with that, of course. If it's got a few that are way high, it gives a bit of a distorted or biased impression there. What about the interquartile range? You might not know much about this. The interquartile range is the upper quartile minus the lower quartile. What's that? Well, quartiles are dividing the distribution into quarters. So we might have the minimum value, then the lower quartile is the value, the score from the minimum to there, which contains a quarter of scores, and then the median is in here. We know that's the next quarter to make the median halfway up the scale, and then we've got the upper quartile, so that's the next quarter. So to the upper quartile we've actually got 3/4 of all scores, and then the max up here. So between these two we've got the upper quarter. So that's another way of looking at a data set, dividing it into quarters. And then we say, well, how spread out is the bulk of the distribution in the middle? Well, not the bulk. How spread out is the 50% of the scores in the middle, trying to capture that middle 50% and see what they're doing. So even that is not complete, isn't it? It doesn't tell us about the upper and lower values very much, just the spread of this middle 50%. We'll have a look at that. And then the standard deviation says something different again. It's the average deviation of data values away from the mean. I think you can see that here. We're finding the spread of this, or the separation of the first score away from the mean, the sample mean, and then square it, and then the second score away, and adding them all up, adding up the squares. And later on we'll see why we actually square that deviation of each score away from the mean. Now this is a new one. I think this is a new one for you. So hang on and we'll have a talk about that a bit later on. Okay, come down now and let's have a look at an example from Hayes and Harris. Find the range of the data set there, searching through the data for the minimum value, maximum value, and taking it away. So that's fairly simple. For a data set like that, we probably don't need a calculator. Okay, we'll see a lot of use of the calculator in this presentation though. All right, what about another one? Here's another example. Pumpkin crop. Now, this is more continuous data now. That was discrete data back there. Find the distribution for the distribution, find the range, the median, the interquartile range. So okay, this is on the calculator now. Let's just revise this. We'll be doing a bit of this down below, but you've got to go to stat mode, don't you? I'll do it on the Casio. Here's a window printout from the TI. Stat mode, into list 1, put the data. Then you've got to hit F2, which is calc. If you hit F2, which is calc, you get graph 1, graph 2, etc. So you then got to go to setup. And if you hit setup, you want the X list or the variable list, list 1, or whatever list you put it in. And because each of these occur only once, you've got to adjust frequency to 1. If you execute that and then hit 1 there, comes up on the left hand side of your screen, you'll get a whole window, won't you? You get X bar, da 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 da, and then down the bottom here, min X, just like we've got here, up here for the TI. Okay, just remembering that calc function. Don't forget to set your calculator up into whatever, or referring to whatever list you want it to calculate these values for. Okay, and then you can just read it off. The range is the max X minus the min, check that. The median, the middle of all the scores, 3.4. And then the interquartile range. The score above which there's 1/4, there it is. And then the score below which is 1/4. Dividing the distribution up into quarters. Therefore, understand the word interstate, between, quarters, here quartiles, and that's the spread of the middle 50%. And distributions can be usefully compared in their spread using that one. Okay, come down, another one here. Jason's a full forward in the local Aussie rules team. The number of goals he's kicked this so far this season is this. So this is discrete data. We want the mean, the median, the range, and the interquartile range. So this time using the Casio, as I said before, stat mode, list 1, enter the data, hit calc, F2 down the bottom, set, and set it up is to referring to what list you put the data in. All frequency 1s, we just list that data straight because it's not a frequency table, and we get everything we need lower down as we come down the screen from the initial page. Okay, so where are the numbers? X bar, well, that was up in the first screen, that was up there somewhere. And then when we scroll down, we've got minimum, maximum, so it's 9 take 3 for the range. Interquartile range, Q3, take Q1, and there we have it. Okay, so we can do it with continuous data or discrete data, and just remember we usually do it on the calculator. Alright, so here's some for you to try. There's 5H, and this is question 1, so you can follow this in the textbook as well. So pause the presentation, have a go. The answer will be coming up down the bottom. Now I'm going to give you question 2 so you can see all of it. There we are. So pause it, have a go. Let's try and get it right. Budding young statisticians, you're getting some skills now. Let's keep the accuracy there. All right, okay, let's have a look at the answers. There they are. All right, how are you going? You might rewind the presentation, just check it out. Let's go on though and see what's coming up. And there it is. Box and Whisker Plots. Don't know whether you've seen these before. Doesn't matter, they're quite good fun. And you can take it all off the calculator. Excuse me. Okay, so this is what I referred to up in the first screen. Picturing the data split into quarters basically. So what do? You draw, first of all, you have a scale here. And this actually should be labelled. What is this? This could be goals kicked or something. Okay, so you make a scale up based on the minimum. So the minimum, you get this from the calculator, plot the minimum opposite this scale unit, and you've worked out it's from roughly 3 to 9, so go from 2 to 10, something like that, a proper scale. And then you mark in Q1, which was 5, so you draw a line here, median, which was 6, Q3, which is 7, all with a ruler. This is a precise graph now. It's a graph, not a little drawing. Maximum is 9. And then you draw your whiskers. So we use a a line or a whisker, then a box for the middle 50%, and then a line or a whisker there. It's called a box and whisker plot. So the bottom quarter, so there's a quarter of all scores here, and the top quarter are whiskered, if you like. Okay, and then you draw your box in the middle here, nice and neatly as they've done there. Okay, and because this is dividing a distribution up into fours, it's actually a 5-number summary. So we need the end, the bottom quarter, the median or the middle second quarter, Q2 if you like, and then the third quarter, and then the max. Okay, remembering these are actual scores on the distribution that divided into quarter pieces. Okay, so you can see your interquartile range quite clearly here. The length of the box, if you like. Q3 take Q1. Now, can you do that? We can do it by hand, but later on I'm going to show you how the calculator produces box plots. Okay, so come down and let's have a look. Here's one done by hand now. Okay, netball, discrete data, 5-number summary. Well, straight into this one and then read it off. Min, Q1, med, Q3 and max. So can we get the range? Yes, the range is easy enough. The range, we are supposed to do a box plot first. Okay, let's do a box plot. We see what the lowest score is about 2 here. The upper score is 9 there. So we want to scale, let's say from 0 to 10. Number of goals. Find the minimum. Okay, find number summary 2. Plot it. Find lower quartile. Plot it. This time making a mark there. Median. Plot it. Q3 is a 7. Plot it. Maximum is 9. And then box that in there with a ruler and a ruler for the whiskers here. And you've got it. Nice diagram. Okay, so what's the range? It's the max minus the min, so it's 9 take 2. Interquartile range, the length of the box, 7 take 4 is 3. And then you can answer some questions. Find the percentage of matches where Peter throws 7 goals or less. 7 goals there. Well, that's the top of the box, and we know there's 3 quarters up to then, so it's 75% of the time. Right, just remembering, each part of this box and whisker plot represents a quarter. They won't be the same widths here. In other words, you've got a quarter of all scores crammed in to a smaller width there. So that tells you something about the distribution. In that box, it's more spread out in the second quarter up to the median than what is in the next quarter. So just remember, the shape of the box here doesn't refer to the quarters, etc. What it refers to is how well spread the quarter of all scores there were over that range of values. Okay. All right, so come down and let's have a look. We're finding quite a bit out about the distributions now. Okay, so the next thing we want to do, we're describing the spread, aren't we? The spread of the data set. So there's something that disturbs our discussion a little bit, and that's if there are a few values way out from the data set. That's going to upset the range, isn't it? If we've got values right out on the ends here, that's going to give a big increase in the range, but yet that's not really appropriate, is it? Because they are outliers, they aren't really characteristic of the data. They generally are thought to represent errors in measurement, and therefore we should look at those separately. So the outliers are extraordinary, not in the ordinary, separated from the main body of data, either much larger or much smaller. So we've got these marks out there. The question is, how far, isn't it? How far out from the data set do scores lie before we say, oh no, they are outliers. We will better have a special consideration and look at whether they are errors in measurement. So we need a rule, don't we, of how far out before we remove them from the data and we look at them separately like we are here. we're saying, well, that's a data set we're going to describe. These others here are a bit far out. We'll have a look at them as whether they're errors or not. Okay, come down and let's have a look. Here's a rule. There are about 6 different mathematical rules for determining outliers depending on your circumstance. But this is a common one, so we're going to have a look at that one. So let's have a look now. Okay, so here's the rule. How far above the data set can you go, the upper boundary? Now, you go to the upper quartile, and then you add 1.5 times the interquartile range. So what they're saying is how far this way do you have to be too far, and therefore call that measurement an outlier. So what do? You go to the upper boundary, you go to the upper quartile, top of the box, and you add 1.5 times the interquartile range. What's that? The length of the box. So what it's saying is you can take the upper end of the box plus 1.5, hang on, let's just get this right here. 1.5 box lengths off the top. 1.5 box lengths off the top. So let's do it. Box length here is what? Well, that's 7 in there. So that lower quartile, 6.5 up to 10. That box length is 3.5. 3.5 units long. Okay, so how far can you go off the top of the box here before it's an outlier? 1.5 times 3.5. Okay. What's that going to come to? Okay, let's have a look. Let's do it on the calculator now, and you can just check it while. And that's 5.25. So, if that's the top of the box, how far this way can we go before we call an outlier? Well, 10 plus 5.25 is 15.25. Let's find it. 15, it's in here. 15.25. That's why they've marked 16 as an outlier. What about on the lower end? We've got one here. So what do you do there? Well, you go to the lower end of the box, lower quartile, and we see if it's too far off the end. Lower end minus 1.5 by the box length. Okay, so what is it here? Come over here. We've got 6.5. So it's going to be 6.5 minus 1.5 times 3.5 minus 5.25. So this goes right down to 1.25. Okay, so how far down here can you come? Well, this is 1, and it's in here, isn't it? 1.25, halfway there. So this one only just misses out. Because it's 1, it's outside the lower boundary. So the upper boundary for a data point to be considered part of the data set and not lying too far away is 1.25 to 15.25. Okay. Have you got it? Let's put down some steps. Getting pretty crowded here. Steps. Number 1. Find the interquartile range. Multiply it by 1.5. So you've got a number. Then the upper boundary, how far up you can go, is Q3, top of the box. Alright, plus the figure from 2, which is 1.5 times interquartile range. So you can't go higher than that away from the data set. And on the lower end, you get the lower quartile, which is Q1, and take away that number 2, 1.5 times interquartile range, and this is off the lower end of the box. Okay, so you've got extremes there. How far above the box can you go and still include it as part of the data set? How far below? And what we're going to say, therefore, if they're outside of that, we should examine those measures carefully as to whether we include them. If they could possibly be errors in measurement, then we exclude them from the data. Do you get it? Okay. You might go back and watch me do all that again later on. Come down and let's have a look at an example. And I brought the calculator on board here. This is very good use of a calculator here. Okay, draw a box plot for the following data, testing for outliers and marking them if they exist with an asterisk on the box plot. So there's the data set, fairly messy to look at. So they've then gone and put the 20 scores in order. Now this is why we might use a calculator in this course, because the calculator will do that for you. But anyway, if you did that, you would find the minimum, the lower quartile, the median, upper quartile, the max. Find the interquartile range, test for outliers. It's the top of the box, 10 plus 1.5 times interquartile range. There it is, 15.25 is the one we just did. And then lower boundary, lower quartile take 1.5, just what we did before. Okay, so these two are outside of that, because we've said you can't go higher than 15.25, and we've got a 16 here. You can't go lower than 1.25 and we've got a 1. So hence the asterisk. All right, that's a lot of work by hand. So what we want to do is to have a look at it on the calculator. So what do? Okay, we've done this before. We go to stat mode, enter the data into list 1. Now I've used a different data set here. Please note it's a different data set. Okay, so when you have hit that, what we want to do this time is draw a graph. So it's F1 there. F1 to choose graph. This window comes up. First thing we need to do is to set it as to a box plot. So that's F6. Okay, and we come up with this screen or something like that. And we want to change it. So we hit that button there and go across the next window and choose Med. So we're on graph 1. We're going to choose Med box. We then have to scroll down and change this here. Well, X list is list 1, but the frequency of each score is only 1. Later on I'll show you if there's a frequency table, you've got to put into list 2 the frequencies to match list 1 to tell the calculator that that's there. Look at this, outliers on. So you can choose those from there. Excuse me. So then you hit execute and it comes back to this window. Now there's one more thing you have to do with the graph mode here. Let's have a look here. You go to select, which is F4, and you select which graphs you want, because you can potentially have 3 box plots on here, or 3 different graphs all at once. So you put draw on for stat graph 1. If you've got 2 and one's in list 2, you can put that on by choosing that here. Then if you hit draw, we get our box plot. Just notice this is a different data set. So we haven't got outliers here. And mind you, our test for outliers is a little bit different for the calculator's test for outliers. So not always will they give you the same answer, but generally they will. Now I want to show you a little trick here. If you do Shift F1 from this window, which is trace, Shift F1, if you go to trace, have a look at what happens. It pops on here, and we can use the arrow button. Here, hang on, I'll just draw this in. Okay, we can use this button and pop across. Okay, and you can get your 5-number summary from there. In other words, sometimes if you're going to draw a graph and you want a 5-number summary, it might be better to just go through the whole process here, into list 1, draw the graph, and pluck your 5-number summary from tracing. Or once you've drawn the box plot, you can hit 1 there, and you get that calculator window, N, min, X, etc. So there's a few little tricky do's here that you can use. But if you want a box plot graph and all the numbers, you might put that into stat mode as we've just done. Draw the graph and don't worry about the calc, the 1 there part. Just pop across on the actual diagram. Okay, and you can draw 3 at once here. by setting up the calculator, come back here as to graph 2 being a med box and graph 3 being a med box, using list 1, list 2 and list 3. Alright, you might study that. Don't know whether you've seen that one before. Calculator is very useful. I'm using the Casio here. Casio 9860 Plus, what a great calculator it is. Okay, come down now and let's have a look. Here are some. There's a graph that's been drawn. I want you to try and work out what's going on with that in question 3. So have a go at question 3 and question 4. And pause it. I'll show you the answers later on. Let's go to question 5. We've got a couple more here. 5 and 6. Okay. Now here's the first one you've got to be careful of. See that? You've got a number of nails and each one occurs a different number of times. So you're going to have to go to stat mode and put in list 1 the number of nails in the box, and then list 2 you'll put the frequency, how many times each of those number of nails occurs. And don't forget then, if you're doing you're doing a box plot, so you might as well go straight to graph, which is F1. Once you've listed those, then go to set, and don't forget xlist list 1 frequency has to be set at list 2. So set on the calculator is important, telling the calculator that you have different frequencies or occurrences of each of those values. Then after you execute that, you can choose select and draw your box plot and take the interquartile range and everything. Well, the 5-number summary could be taken off the box plot if you want, or you can go to calc. But the value of this graphical approach in getting your box plot is you'll have a picture of the box plot from the calculator for a start. Okay, think about how you might want to do that. Do it both ways. See what you think. All right, pause it, have a go, and I'll show you the answers now. Okay, 3, 4, 5 and 6. Getting powerful now, getting some good tools together. The idea, of course, is people don't like lots of numbers. Excuse me. They like graphs, but they also need to have an interpretation. What's about the middle? In this suburb, what would I be likely to have to pay for a house? What range do they range from? What's the cheapest? Lots of things we have to tell people about data sets. They generally don't like to fossick through numbers by themselves. All right, let's keep going. Let's build up. Oh, here's one. Here's an interesting one. I might have confused you earlier when I was talking about the standard deviation. Now, later on in this course, this becomes very important in normal distributions and distributions of continuous data in an applied way. So we'll wait and see that then. But let's define it now. We have already. It's the average deviation of data values from the mean. Okay, and probably says more about the whole data set than the interquartile range does. So here we are. If we take a sample, n in the sample, standard deviation is the sum of all the deviations of all the scores away from the mean. So you get all your scores, you find their mean, then you take each one away, square it, add them up, and find an average. Well, it's n take 1. Rather than n. Now that's beyond this course to actually explain why. It's called degrees of freedom. 1 less degree of freedom. And then you take the square root of those squares. A good question for a budding young mathematician might be, why do I square them in the first place if I now have to square root them and undo all that stuff? Well, we're going to talk about that in a minute. Now, if you take the whole population, right, remember this S over here is called a statistic. It's calculated from a sample. That's why S stands for standard deviation as a sample measure. And if you took the whole population, that is the whole n of them, and you knew the population mean, the actual parameter, remember this is called a population parameter, when you're working with the actual value from the population, the actual value. You're not estimating it with a statistic. This is from a sample. Remember Huddy's favourite drawing, the population here, and we're trying to represent it often because it's too big. We're taking a lot of data points from there, taking a sample, and we're going to use that sample to describe the population. That's quite often what we have to do because the population is too big. But if we don't, if we can actually measure the actual standard deviation of the whole population, then we would be using the actual mean, and we'd have the same sort of formula. This is the sum. Remember here, this might not seem that much. That means the sum of, in mathematics, Greek capital sigma used for sum. So that's summing all the scores, all the members of the population, deviation away from the mean, taking away the mean. Now I want to pause there just for a minute and just think about that. If you had a distribution, let's say we had a distribution here, and we're going to measure the standard deviation. So the mean's somewhere in the middle. This is a sample that we've taken. The mean would be in the middle, wouldn't they? Be sort of balancing out with the symmetry on either side. Now let's look at what happens if we take various scores from that distribution. Have a look here. Let's take one there and we measure its deviation, x1 take x bar, away from the mean. Let's take another one over here. Its x1 take x bar is going to be negative. This is bigger than the mean. You take it away, you get that. That's going to be a positive. x2 take x bar. What have I done to confuse things? I've taken one equidistant from the mean on the other side. So that's going to be negative, the same value. So if the distribution is symmetrical, and these are the important distributions in which we want to use a standard deviation, and you'll find that out later on, symmetric distributions. Can you see that just taking the mean away from the score to find how far that score is away from the middle, they're going to cancel each other out. If we add them, you'll get naught. Because this one is the same distance to the right as this one is to the left. Because you've got a symmetric distribution. So the sum of all the deviations would come to 0 in a symmetric distribution. Well, that's no good. We're trying to measure the spread of the distribution away from the mean. So the little tricky we do is to square the deviations. So that this one becomes a positive like this one, and we're going to have a realistic estimate of the deviation of the scores from the mean, albeit they'll be squares. So that's why there's a square root in the formula at the end. See this? xi take x bar squared on n take 1. We had to square them all, otherwise in a symmetric distribution they all cancel each other out and have no deviation at all, which is ridiculous because you've got some above and some below. Trying to measure how far away from the mean in a symmetric distribution the scores are. So we had to square them, and then we reverse that by a square root. So it's an estimate of the individual deviations of the scores away from the mean. It's a frightening looking expression up here, but it's not really that hard to see where it came from. All right, let's go on and see if we can do something with that. Here we are. And I've used the calculator down below there again. So just watch this. The green grocer purchases oranges from 2 different wholesalers. They take 5 random samples of 40 origins to examine them for skin blemishes. The counts for the number of skin blemishes are, okay, from the 2 manufacturers here. So this is first manufacturer, second, or not different wholesalers. Find the mean and standard deviation for each set and hence compare the wholesaler suppliers. Okay, so you'll put the first one in list 1, second one in list 2. This is in stat mode on the Casio. Okay, if you hit execute, you get this window. So you've got to set it up, and you can only set up one at a time. So let's do wholesaler 1 first, healthy eating. So it comes up list 1, make sure the frequency is 1. It's not list 2, that's a different wholesaler. So it's just one variable, so you don't need 2 variable stuff here. If you hit execute, then all right, you've got to hit execute, and then I've forgotten to tell you back here we should have hit calc, sorry, to get this window. If you hit execute and hit one there again, then you get this window, and you can keep scrolling down to get the other things you want. But at the moment, all we want is the mean, which is x bar. And the standard deviation will be this one, not sigma x, because you're only taking a sample. So this is the sample standard deviation. This one here is the population. We haven't done the whole population of oranges from these two wholesalers. We've taken 40. Okay, so there it is there. You would use SX. Mind you, I haven't used all that data set there. No, we've got 5 points in the data set from the 40 oranges to look for our skin blemishes. Okay, so there you are. Watch out on the calculator. That one, not the sigma one. All right, are you ready? Let's have a look. Got a few there. Excuse me. I'd like you to pause the presentation and have a look and look at the data set carefully as to how you're going to handle it, and then follow through. So there's 8 and 9. Pause it and have a go. Look at question 10. And I'll bring up 11. Okay, let's have a look at those answers now. There, how did you go? Just watch this question here. Why is the standard deviation the only useful measure of spread in that one? Think about that, discuss it with your classmates and teacher. Let's go on and finish off now. Okay, so this formula looks a lot like the other standard deviation one for a sample, and it is. It's just got an F there. Right, in other words, when you have a frequency table, each test score occurred with a frequency. You can't just put these in to list one, because they all occurred a different number of times. The frequency was not one. So let's just revise the calculator where you have a frequency table. So again, go to stat mode, list 1, test score, frequency list 2, and what do we want to do here? We want to do some calculations. So you hit calc, you get this window, hit set, list 1, and no, we don't want that. We've put our frequencies in list 2, and they aren't all equal at 1, so hit list F2, you get this window, and if you enter 2 in there, we come to this one down the bottom here, just what's down here. So that's our test score and that's our frequency. Okay, and if you execute that, you come back to this window and you can hit F1, one there, and up comes everything you want, including going down page to get into quartile range and things like that. So we've got the mean, and here's the standard deviation score, using that data set and making sure you show, come up here, the calculator that each score is occurring a different number of times, and not just single scores. It's been put in a frequency table. So are you ready? Watching for the difference between single points in a data set versus a frequency table. Don't forget to set this up here. Here it is. Don't forget to set it up as to list 1 is the data and list 2 is the frequency. Okay, come down now and let's have a look at some problems for you. Okay, 12, 13 and 14, they are all frequency tables here, so set your calculator up carefully. Okay, come down and let's look at the last one, 15. And I want you to have a go, get excited, draw good graphs, make sure your technology's there. In the workplace, however, you'd use Excel, a computer program, but for this work at the moment, introductory, we're using a calculator. Okay, let's look at the answers now. There they are. And you've finished this presentation. I think you're going to graduate very well if you keep working this hard. Now, there is more. There are coming up in a few more presentations on this statistics at this level. So I hope you're getting excited, because there are some other exciting things coming up. And what I'll say for now is cheers. Catch you later on.